So now we have such a pointer. What can we do with it? Well, for example, we can use it to still get the value at which the pointer is pointing. Keep in mind, here in line 14, I'm printing the pointer, and if we run this module, we therefore get the address, because I'm printing the value stored in this variable, and that value is the address of age. Hence, we get the address here. But if I want to print the stored value instead, we can get access to that again with the address here by adding an asterisk in front of this variable. We saw that asterisk before on the type when we created the variable. We can also use it in our code if we have an address and we want to get the value stored in that address. So we have ampersand to get the address of a value, and we have asterisk to get the value stored in an address. So basically to reverse that operation. And therefore now if I save this with the asterisk added here in line 14, if we run this code again, we now get 32 here because we do now get access to the stored value. This process, by the way, is called dereferencing, because we're diving into that address and getting that value. We can also not just read values with help of pointers, we can also assign values. So, for example here, we could use myAge and store a new value in it. Now here you have to be careful. If you try to do something like that, you will get an error if you want to store 33 in myAge. Why? Because myAge is a pointer. It's not the value itself, it's the address of the value. So in myAge, we are only allowed to store addresses. Now 33 is not an address, it's probably the new value we want to store in that address. But then we can't assign it to a variable that only contains the address. And that's basically the error we get here. We can't store that integer in a place where the address of an integer is expected. As a side note, in other programming languages like C++, for example, you can do something like that, and you can then change the address stored in a pointer like that, but that can also often lead to problems where you accidentally change some address. It can also lead to security issues, and therefore Go does not allow that. But how could we now change the value stored in that address? For this, we again need to dereference our pointer. We can again add an asterisk here, and if we do that, we tell Go that we want to change the value stored in the address stored in myAge. And we want to set the value stored in that address to 33. And therefore, if we then print myAge thereafter again, and I don't mean myAge itself, but we dereference it and we print the value stored in myAge, then if I again run this module, we print 33 here in the end because we changed the value here. By the way, what do you think would happen if we don't just print the dereferenced myAge, but we print age itself? So the variable which we created here at the very beginning. What do you think do we get if we print age here at the bottom of the main function? Well, let's give it a try. If I run this module, we get 33 as well here. And that shouldn't come as a surprise because we're working on one and the same value. We created the variable age, then we got the address of that variable, of that value stored in the variable to be precise, and we stored that address in myAge. And then we used that address to assign a new value to it, so to overwrite the value currently stored in it. And therefore, of course, age now also has that new value, because age and myAge in the end are referring to the same value in memory. The only difference is that myAge only holds the address, and we explicitly need to reach out to the value with help of the asterisk. Whereas age does also know the address, but automatically works with and on the value whenever we use that variable. So here we don't need to explicitly reach out to the value when we work with age. But we are working on the same value stored in the same address in memory in the end. And that's how pointers work. But of course, with this very basic example here, it's still not really clear why we might want to use pointers. After all, pointers are just a bit more complex to work with. We always have to add that asterisk, and there isn't a clear advantage of using pointers, right? Well, this was just an example to understand the general syntax. Now I want to show you what you can do with pointers and with that concept of having the address instead of the value. So let's explore why we might want to use pointers, though I want to say right away that the real good use cases will come a little bit later once we also learned about other important Go features. Nonetheless, let's see an example here right now. Let's say we have a function called double here, which takes a number as an input, as a parameter, which is an integer, and which should return an integer. And in that function, we might just return number times 2, which will double the input number. Then, of course, here in my main function, I could create a doubled age variable by calling double and passing age, so not the pointer, but the age variable itself, which stores the value itself, to double. And then thereafter, we can, of course, print doubled age like that. Okay, if we do that, it should not be too surprising that if we run this file, we get 66 as our output in the end, which is simply our current age, 33, before this line times 2. Now, what happens here, if we have a function like this that takes a parameter, is that whenever this function is called and a value is passed as a parameter value, like age here, Go will go ahead and copy that value. So it will create a new entry in memory and store that value in that new entry. So if we before had one place in memory where the age was stored, we now have two places. One for the original age and one for the new age. And we can tell that this is the case if we add a result variable here, in which we store number times 2. And then after doing that, we set number equal to 100. And then here I only return result. If I do that and the number would not be copied, so we would get the address of age and we would work on that same value inside of this function as we work on in the main function, then changing number to 100 should actually ensure that the number we pass in is 100 after we called this function. So if I print my age thereafter, this should be 100 if Go would not create a copy of age inside of this function. So if you would operate on the same value in memory, then age should be 100 here, because we override it here inside of the function. But as you can probably already tell by the way I am phrasing this, if we run this module, we get 33, not 100. Because Go is creating a copy. And it has good reasons for doing that, because this ensures that inside of a function, we can't accidentally change a value defined in some other place of our code. If we call the double function and we pass age to it, we can't accidentally change age from inside this function. We only change the local copy of the provided value, and the original value is not stored. Now, that extra place in memory that is occupied is of course freed up once the function execution finishes, because then this number variable is not being used anymore, because it only exists inside of this function. So then it can be garbage collected. But still, during that function execution, we have that copy. And this is not bad. As I just explained, it is a behavior that makes sense. Now, for numbers, this will also probably never be a problem. But we will soon learn about more complex data structures beyond numbers and strings. More complex data structures that can take up more space in memory. And if such data structures are then copied, we have two big data structures in memory, And depending on the kind of application you're building, that could then actually lead to a lot of memory being occupied just because you're calling a lot of functions. And that can make your program slower. Again, definitely not the case here for a simple number, but for more complex data structures, that is a problem into which we can run. And now that is a scenario where pointers could help us. If in double, we don't expect the value, but instead a pointer at a value, so we expect an address, then Go won't copy that value. So here we can make it clear that we want a pointer by again adding this asterisk in front of the type. Now double wants a pointer at a value instead of the value itself. So when we call double, we no longer can pass in age, which holds the value itself, but we should pass in my age, which holds the address. So which is that pointer? And my age like this, not with an asterisk in front of it, because we don't want to pass in the value, but really the address itself. So that here we get the address of a number in the end. Now, we shouldn't change it, of course, here, and we can't change it, so let's get rid of that dummy line. And we, of course, now also need to dereference it if we want to work with the value. So here, when we derive the result, we need to add an asterisk in front of number to get the actual value stored in that address, so that we can then perform this operation on that value. But now, whenever we call double, we'll not copy that value in memory and occupy new space in memory. Instead, we'll just pass the address into that function, and then in here we work on the same value as we have it here in the main function. And therefore, if that would be a more complex data structure, we avoid that possibly very expensive, from a memory perspective, this very expensive duplication. Now, if we save this and we run this program again, we get the same results as before, but we have this possible performance gain. Now, that was one of the two advantages, or potential advantages, of pointers. Another advantage could be that we can now edit the original value from inside a function. Before, this was not possible because we got a brand new copy. And as we saw a couple of minutes ago, if we tried to change that, if we tried to change it to 100, that had no effect on the original value. Well, now, since we get the address, we can, of course, change the original value. Here, I could now reach out to the value stored in number by adding the asterisk at the beginning and set this to 100. If we do this and we now run this module again, we get 100 here at the very bottom for this print line statement here, because we did change the original value because we got its address here. And through that address, we can access that original value from inside this function. Now, sometimes this can lead to horrible bugs and you want to avoid it. But sometimes you also have functions that should indeed manipulate the original value. Again, it's most useful if you have more complex data structures which you might want to manipulate from inside functions. This here, of course, is just a dummy example which has no real purpose. But with that, you still hopefully get an idea of what pointers are and what you can do with them. Now, throughout the rest of the course, where we will now explore more advanced features and more complex data structures, it will also become more obvious when and why you might want to use pointers. You definitely don't need them if you only work with simple integers or strings, as we're doing it here. But now we got the foundation to dive in deeper.